So this is homework 6, problem 5a. We're being asked to consider this Hamilton-Jacobi equation with the following initial data. And we're asked a few things. Firstly, show that characteristics collide at x equals 0 starting from time 0. Then find a solution using the characteristic method of characteristics and compare with the solution that you get from the Hopflax formula. So let's just get started. If we apply the method of characteristics, we get the following. So x dot is equal to spatial derivative, px dot is equal to 0, and z dot is equal to this. So firstly, this second equation just implies that the spatial derivative is constant along the characteristics. Um, and px0 is just the spatial derivative of u evaluated at x equals 0. We're given that the initial data is negative absolute value of x. So this is just this. So this isn't differentiable at 0, but everywhere else we can find a derivative. So this is 1 if x is less than 0 and negative 1 if x is greater than 0, right? Because the graph of this is kind of like this. Then if we look at the first equation, that tells us that our characteristics are of this form. So this will depend on where the characteristic starts. If it starts on the left half of the real axis, then it'll be t plus x0. And if it starts on the right-hand side, uh, it'll be negative t plus x0. Right, so we sort of have the following picture. So if this is a space-time diagram, then our characteristics look something like this. So what this tells us is that for arbitrarily small time t prime, let's say somewhere here, we can find characteristics that collide at 0 comma t prime, namely the characteristics x of t is equal to t minus t prime, right? That's this one that starts here. And the characteristic negative t plus t prime, which is the one that starts over here. All right, so for arbitrarily small time, we can find characteristics that collide along x equals 0. So now to get a solution, we can just reconcile this by saying that there's a shock here. So it's clear from the picture that a shock starts at 0, 0. And by ranking Huguenot, we get S dot is equal to 1/2 U minus plus U plus. So U minus is the speed of the characteristics that hit from the left. That's going to be 1. And U plus is the speed from the right, which is -1. So this is just 0. So all in all, that tells us that S of t is stationary and stays at 0. So then if we want to solve for U, we can go back to this equation. So we can rewrite z dot as follows. Right, and by the PDE, these two terms are just zero. And we showed earlier that px is constant. So this is just equal to px at zero. And furthermore, we showed that px only takes the values plus or minus one. So plus or minus one squared is just equal to one times one half. So then that tells us z of t is equal to t over two plus z naught. Right, z naught is just given by the initial data, which was absolute value of x. So this just then becomes absolute value of x naught. Right, so then for a general point xt in our domain, well, let's call it x prime t prime. We want to find the corresponding characteristic that hits it. So if we're on the right-hand plane, sorry, the upper right quarter plane, then this gets traced back to a characteristic starting here. These have speed -1, so it follows that this initial condition will be x prime plus t prime. On the other hand, if our point is in the upper left quarter plane, then this gets traced back to a characteristic over here. And these have speed +1. So this initial point is going to be x prime minus t prime. All right, so all in all, x naught sort of as a function of x and t is equal to x minus t if x is less than 0, and x plus t if x is greater than 0. All right, so then taking our parameterized solution z, we can unpack this to get the full solution u. So this was t over 2 minus x naught. So in the first case, x naught is x minus t. And in the second case, it's x plus t. All right, so this is pretty much the solution. But we're also asked to compare with the solution we get from the Hoff-Lax formula. And so for the sake of making that comparison easier, we can continue to rewrite the solution that we have here. So note, if x is negative, then oop, then x minus t is also negative because we're taking positive time values. So absolute value of x minus t is negative of x minus t. And similarly, if x is greater than 0, then x plus t is also greater than 0. So its absolute value is just itself. Right, so then this can be rewritten. So this first piece gets an additional negative sign in front of the x and the t. And for the second piece, these absolute value bars just become parentheses. So we get t over 2 minus t over 2. Sorry, t over 2 minus t, which becomes minus t over 2. And then we get a plus x here. And in the second case, we again have t over 2 minus t. So this becomes minus t over 2, but this time with the minus x. All right, so this is the solution we get from method of characteristics. So now we want to see if we can get the same solution with HW6. So just writing the formula, this is equal to inf over all y and r of t h star x minus y over t minus sorry, plus the initial data evaluated at y, which is minus absolute value of y. Right, so h star as a function of v is equal to the sup in p of p inner product with v minus h of p. So we're working in R1. Our spatial domain is R1, so this is just a product of two numbers. And h of p is half p squared. So this is a concave quadratic. So this sup is realized at its critical point. So DDP of this thing is v minus p. So the sup is attained at v equals p. Sorry, rather p equals v. Same thing. So this is equal to v squared minus half v squared, which is equal to half v squared. Right, so then u of x is inf y and r of t over 2 x minus y over t squared minus absolute value of y. And this is 1 over 2t x minus y squared minus absolute value of y. Now, it would be really easy to find this infimum if we didn't have these absolute value bars. So what we can do to sort of get rid of them is to note that the infimum over all of R is just equal to the minimum between the infimum over non-negative y and non-positive y. Sorry, non-positive and non-negative, but uh, same thing. Um, right, so let's first find these two things. So for y less than or equal to 0, we're looking at this thing. So if y is less than or equal to 0, then absolute value y is equal to negative y. So then this just becomes this. And this time we have a convex quadratic. So its infimum is realized at its critical point. So 0 is equal to d dy of this thing. This is equal to negative 1 over t of x minus y. And this negative is coming from the negative in front of this y. So then just solve for y. This should be, let's see, x minus y is equal to negative t. So y is equal to x plus t. Sorry, let me make sure I have the signs right. Sorry, this should be a plus. So then our infimum is realized at x minus t. Right, so then this inf is equal to the function evaluated at x minus t. So this becomes t squared, and this becomes x minus t. So t over 2 plus x minus t, which is equal to this. And then we can just do a similar thing for y greater than or equal to 0. So in this case, if y is greater than or equal to 0, just flip these inequalities. Now absolute value of y is just equal to y. So this time we have a minus sign in front of this thing. This is still a convex quadratic, so we can just find the critical point. And this time it's sorry, this is not squared. So we get negative t is equal to x minus y. So y is equal to x plus t. Right. So this inf is realized at x plus t. So t over 2 minus x minus t. So t over 2, sorry, negative t over 2 minus x. Right, so then just reiterating what we did, ux of t is equal to the infimum of all y and r of that function that we wrote earlier. We argued that this is equal to the minimum between the infimum over y less than or equal to 0 and infimum over y greater than or equal to 0. And we just computed that this first inf is negative t over 2 plus x. And the second inf is negative t over 2 minus x. Right, so now we have to determine which of these um, is minimal. So both terms have this negative t over 2 in common. So the minimum is decided between which of plus x and minus x is smaller. So if x is positive, then minus x is smaller than x. But if x is negative, then x is smaller than negative x. All right, so this min is equal to, uh, yeah, so we're minimizing negative t over 2 plus x if x is less than 0. And negative t over 2 minus x if x is greater than 0. All right, so this is just our solution from Hopflax. And if we look back at our work, uh, the solution we got from method of characteristics, this is exactly the same thing.